Please go ahead.
Okay, so this is the outline of my talk. First, I will introduce neural ordinary differential equations, which is the backbone of all of my works which I've done in my PhD. And for neural ordinary differential equations, I will give introduction about the basic concepts like what is ResNet, ODE, relation between among both ResNet and ODE, and some of the numerical methods. Followed by, I'll just give some summary of my two chapters of my thesis, followed by detailed discussion of two problems. So I guess you're already familiar with the architecture of ResNet, why it was proposed, as ResNet architecture with its skip connections help to improve the generalization performance of deep learning models with increasing the number of layers. And this is a simple residual block, as you can see. And you can
Sorry, Srinivas, are you sharing the right screen? We are still looking at your first page of your PowerPoint.
oh, still on the first page, sorry.
And maybe you are sharing the wrong screen with us.
Okay. Can you see now? ResNet.
Yes.
Yeah.
Okay, sure. Okay, again, this is the outline. I think you got the outline, what I'm going to discuss. So, a residual network, as you know, there is a skip connection. And this ResNet can be like, you can increase the size of the depth of the ResNet network by stacking multiple residual blocks of different multiple channels. The dimension could vary. So now I'll give a brief introduction about ordinary differential equations. An ordinary differential equation is given by the following expression, where y is considered to be the state. The state could be the motion of an
Are you
object.
moving to next slide? Well, keep seeing your
Oh,
slide 3.
you didn't see this ODE slide?
Is that only me or someone? Oh, okay.
Yeah,
Okay.
it's just having a lag. Could you switch to the slideshow mode? I think that might help.
Yeah, okay. Now, is it ODE is visible?
Yeah, we could see the ODE, but it took a
Okay.
long time to bring it
Sure.
to the screen.
So I just changing the slide. Can you see the numerical method slide?
No. Yeah, it came now. The numerical methods.
Now again I change the slide.
Yeah, now it comes. I think we can work it out, I think.
Okay. So here I'm just give what is ordinary differential equation. Ordinary differential equation, it's the change. It's a function like how it is changing over the period of time. For example, in nature also we can see, for example, when we want to calculate the motion of an planets, okay, it can be given in differential equation. So let's consider a simple differential equation of this form. uh, Given its initial state and was solution. I mean, for some of the differential equations, ordinary differential equations, we can compute the solution. What is the solution? It gives, for example, when you give a time, what is the position of the object? So we have the derivative at that point. The solution is nothing but the exact position or exact state of the thing. So this is called initial value problem. What is initial value problem? We have a differential equation, ordinary differential equation, and also a given state, the starting point of the object. Can we build a solution given this two things? This is called initial value problem. And this IVP can also be written as in this way, where y0 is the initial state, and we want to compute the state or the motion of an object at a particular time, capital T. This is can be given as in this way, and you can see there is a definite integral is involved in this computation. So because of this integral, there are many functions which cannot be have a closed form solution. For example, our neural network. So we go for a numerical method. Okay. So Euler is a first order and a very simple numerical method, as you can see here. There are also like higher order numerical methods also exist, like Ranjikuta, fourth order, third order, second order method. As you increase, these are all
I think your
up.
slide didn't move again.
Oh,
Are you having multiple? Okay, yeah, maybe. Yeah, yes, now you are on the new slide.
okay, or else I will stop the slideshow. I just keep in this way. Okay.
Are you sharing a screen or is it just this particular screen?
This particular screen window, this particular window.
Did you try sharing the entire screen?
Okay, I will try again.
Yeah, I think the lag
No,
should be gone now. Can you go back and forth?
can you see the slide?
Yeah, I can see this. Just can you go back and
Okay,
forth
okay,
so
okay,
we can, yeah, it's now
okay,
working. Great.
okay. That's great. So I was just giving the. I think you followed the slides. I hopefully just giving the introduction about ODE. That, and I was saying that not all the ODEs can be the closed form solution can be computed. So we go for numerical methods such as Euler, which is the first order approximation of the Taylor series expansion of the differential equation. And these are there are higher order numerical methods such as RK4, RK3. And the higher the order, you better you approximate the solution with less error margin. But it involves more computation. As you can see, there the function has to be evaluated at different points. So there is an involvement of lot of computation. And there is another parameter called h. H is the step length. I will so here uh, as you can see, there is a blue color line, which is the true solution. This is a solution of the differential equation, which I showed earlier. Uh, and this is a solution. As you can see, for Euler method, it's not approximating the solution. It is not close to the solution at every point, at every time. When you see, you can also observe that when there is a sudden curvature at the solution, Euler starts to deviate from the true solution. But whereas RK4 method, it truly approximates the solution. And we can also make Euler to exactly compute the solution as RK4 by decreasing the step size. But it involves a lot of computations. So this is the drawback of fixed step size numerical methods. That is, if we, for example, uh, from steps 0 to 6, it is kind of a constant. The evolution of the function is kind of constant. Here, higher step size is also fine. But when there is a curvature, if we use a higher step size, it might deviate from its true solution. So here we need to take a smaller steps. So can we have an algorithm such that it adopts according to the curvature, takes consider into the curvature or some other way. So the step size can be varied so that the number of computations can be reduced. So until here is fine. Here I want to introduce about main motive of adaptive step size numerical method, which is the backbone of our neural ordinary differential equation. Any questions until here? Okay. So the adaptive numerical solvers, what is the motivation, the intuition behind the proposed adaptive numerical methods is that as we have shown that the higher order numerical methods, when we with the same step size, let's fix a step size, and you are computing the solution using RK4 and RK3 method. And RK4 method, the solution computed by RK4 method is closer to the actual solution compared to RK3, right? So let's say we computed two different states using RK4 and RK3. Okay, if the error, what we have computed, like y4 is the solution computed using RK4 and y is the actual solution. If both the errors is low, then we can say that y4, the difference between y4 and y3 is also low. So uh, if we start from so we can say that, I mean, for example, if we don't have the solution, if the error between y4 and y, difference between y4 and y3 is low, then we can also say that the difference between y4 minus y and y3 minus y is low. So in this way, we don't have to have the exact solution to figure it out, okay, whether my method is working properly or not for that particular steps. If the difference between y4 and y3 is low, we can say that, okay, for this particular step is enough to find the exact solution. So this is a pseudo algorithm for adaptive solvers. Okay, let's say our T is the capital T, where we want to find the exact state of our differential equation. Okay, and let's say H is the current step size, and for this moment, let's say y4, we computed the current state, which we designate it as y4 and y3, and there is another hyperparameter called tolerance, so which is looking at the absolute difference between these two states. If the difference between these two states is greater than that tolerance, so we can, so this step size is we have to reduce the step size. I mean, having this high the step size is not enough to compute the exact solution which is closer to the actual solution. So then here we reduce the step size. So it's an iterative one. Now, once if the step size is accepted, we accept this step size and store the current state, and we increase the step size. So here we are not fixing to a particular step size. We are kind of exploring smaller step size, larger step size. So in this way, adaptive solvers work.
The TOL means tolerable error or something like that.
Yeah, tolerance error. It's like an hyperparameter.
Yeah.
Yes.
So I mean, when the error is bigger than tolerance error, then you halve your step size.
Yes, of the step size. Yes. Okay. Okay. A Doprify is an fifth order numerical method. It's a kind of they combine both RK5 and RK4. They cleverly here, see, for we have to do RK5 and RK4, for example. But Doprify, it cleverly combined both RK5 and RK4 method to do the same exact thing what this pseudo algorithm is doing. Okay, and here you can see a Doprify, although it is taking taking the number of steps, but is exactly overlapping these points. These are the time steps where we computed the solution. It is exactly overlapping with the exact solution, true solution. As I said earlier, uh, uh, when there is the solution is there is not much curvature in the solution, we don't have noted there is no need of a smaller step size. A larger step size is fine. So here we can see when there is a solution is kind of constant, that step size is kind of larger, and when there is a higher curvature, the step size is smaller. So it is adaptively adjusting its step size over the time. So now coming back to, uh, we will see the relation between our ODE and ResNet. Again, ResNet, the basic building block of this is the residual block, right? Where there is a skip connection. and the skip connection where F is our neural network, which is parameterized by its weights Wi, and this is a skip connection. So I can rewrite this as in this form, right? Instead of y is here, it is the y1, and x there is a y0, and h is the step size, and h is in our skip connection, it is 1, right? So this, if you look at this expression, it looks like a Euler method with step size of 1, where f is our uh, ordinary differential equation with parameterized by its weights theta or wi. So once we treat f as an ODE, we can use any numerical method. Like instead of this just simple skip connection in terms of our deep learning architecture, the connections could be in like something in a different way. So this is the paper which proposed this continuous. Okay.
I think if you go back to the previous slide, F here, you want to treat F as neural ODE, right? Okay, I see. Now I see the connection between neural ODE and the diffusion
Yes.
techniques.
Okay, diffusion techniques.
From that guy mentioned from Professor Liang's group, because
Mhm.
then your F can be the backward policy from the
Yeah.
diffusion. Okay, get it. Thank you.
Okay, sure. So this the neural ordinary differential equation, these were the first people who proposed this continuous transformation. So here in the previous thing, I can use adaptive numerical methods to write, like Doprify. So that is why it is called continuous transformation or continuous evolution of our neural network. And here, unlike ResNet, the parameters are shared across the time. Okay, and here generally the of initial step size is nothing but, for example, here is the given input, and let's say it's a CNN architecture. It computes some hidden representation, which we call it as a hidden initial state with t equal to 0. And the as you remember, there is an hyperparameter called capital T. It generally kept it as 1, and the hidden representation are computed using any numerical method. After getting our final state, it is given to a fully connected neural network followed by any softmax and the traditional backpropagation. So this is the node architecture. So this, in short, as I said, I will explain two of my problems in a very short way. This is one of my work. Earlier, in the previous work, it was shown that neural ordinary differential equations are robust to adversarial attacks compared to the traditional ResNet models. So, and there is another deep learning concept called Gaussian process. Gaussian process or the non-parametric Bayesian models. They are also robust to adversarial attacks. But the problem with GPs are that they can work only on low dimensional data. So what we suggest is that, okay, combine both of these worlds like neural ODE and GP. So until the first part is the neural ODE and the second part is the GP, uh, we just wanted to evaluate how the robustness of this model is and also uncertainty modeling capabilities. So we try to evaluate on different variations of architectures, and this is the different models trained on CFA10 dataset, and we are evaluating on FGSM adversarial attacks. As you can see, with increasing the strength of the adversary, these two models, they have much better robustness compared to the other models, right? So here we showed that, okay, combining both the worlds of neural OD and GP, we can build a model which is robust to adversarial attacks. And I have for other different experiments in the paper. And this is one more paper which was accepted at AAA. If you remember, in the neural OD or other papers, the T is considered as an hyperparameter, the end time. So what we thought, what if we assume there is a distribution over the latent time in T, considering this as a latent variable, learn a distribution over the end time T. So here is the, let's say this Q is our learned posterior or approximate posterior. So the end goal is something like this. So during inference, what we do, uh, okay, this is our learned distribution. Let's say because we took gamma as the distribution, and these are the n times which is sample from the distribution, and we use the average and standard deviation using the computed final predictions. So this kind of model, where like in traditional Bayesian neural networks, if you look at it, we learn the distributions over the weight parameters. But learning a distribution over the entire weight parameters, it's kind of a complex and also time-consuming thing. Here we just learn the distributions over the hyperparameter capital T, and we see that. So the goal of Bayesian learning is that when you make a prediction, away from the training data, your model should exhibit higher uncertainty or lesser confidence. And you can see this is the toy data set. These red points, the points which are in red color, are the training data points, and these points which are in the blue color are the away from the training data point. As you can see, the uncertainty exhibited by our model is lesser for the training data and higher for the samples which are away from the training data. So indeed, this LT node model is behaving like a Bayesian neural network model by learning only the distribution across the late n time t. So here, this is another work, continuous depth recurrent neural differential equation. This part of the work got accepted at ICML workshop, and the full paper got accepted at ECML conference. So traditional RNN models, traditional recurrent neural network models, does not consider inter-arrival time. If you look at any RNN model, we know that the observations are coming at different time steps, right? But in general, the naive RNN model doesn't take into account the inter-arrival time between two observations. So we can say that the standard RNN, the hidden representation, irrespective of the time difference or the inter-arrival time between two observations, the hidden representation is kind of constant. It doesn't affect. So people have as proposed this ODE RNN, where the intermediate transformation is like acts like a neural ODE. Okay, until this n times, although it is GRU or LSTM model, but there is also an evolution of the hidden state, which considers the inter-arrival time. So these are called, there are some data set called irregularly sampled time series data. For those data set, compared to standard RNN models, ODE RNN models shown to perform well. So in our work, what we want to propose is that, so you also know about the stacked RNN model, where multiple RNN blocks are stacked over above each of one. So we want to design a continuous depth RNN model, where it is evolving continuously across the time dimension and also continuously evolving across the depth dimension. So we want to just using this model, does the performance of the model improves or not? So if you look from the perspective of a differential equation, it leads to a problem of solving a differential equation with two independent parameters. So this is like solving a PDE, partial differential equation. So we post solving this problem as solving a partial differential equation, and we looked into the literature of the partial differential equation, how the numerical methods are, what are the numerical methods exist in PDE, and we applied those methods for solving this problem. So one part of our this continuous RNN is a model which is inspired from the heat equation. So heat equation, so generally what is happening in nature, like let's assume a rod. As you can see, it's a rod, and you applied temperatures of varying temperatures T1, T2, T3, T4 at different points. So over the time, the temperature you know that temperature flows from the hotter regions to the colder regions. So over the time, the temperature is moving towards the colder regions, and at a fixed amount of time, it kinds of becomes in an equilibrium state where the change in the temperature across the length is kind of smooth. So here, how we how we use these principles, how we translated this principle into our continuous model is in this way. The temperatures which are applied at different points, like as is shown in the previous figure, L1, L2, L3, assume this as the arrival of observations at different point, T1, T2, T3. Okay. As the temperature applied at a point will affect its immediate neighbors, the hidden states computed are affecting the data points in its neighborhood. So this is where one-to-one analog comparison of the heat equation and how we want to uh, um, build our continuous depth models. So we know the heat is evolving across the time, over the time. Let's say it is T dash. Here, the evolution of the hidden states over the depth. So this is the how we inspired ourselves. Generally, this is the heat equation, but we consider the non-homogeneous heat equation of this form. Here, F is a GRU cell, and we used two
Sorry,
different
sorry,
numerical.
can you go back
Sorry.
a bit? Where did you? Oh, okay. This is no different. Okay, here we go. Okay,
Okay.
good. Yeah.
Sure. So we try two different numerical methods. One is finite step method, and another is multi multi-step numerical method. Here, okay, visual how this finite step method, we can rewrite this differential equation, okay, in a discrete form, and after arranging the terms, we get the next state. How to compute the next states given its neighboring states. So this is the pictorial representation of computation of the hidden states. So in this way, over the time, we compute the hidden state across the entire grid, and we evaluated our model and compared with the existing baselines for three different data set. Here I am showing for two different data set where person activity recognition, which is the classification, and Walker 2D kinematic is a regression problem. For this both the data set, our models, two different models with two different algorithms are working better. So this shows that, okay, assuming a continuous evaluation of transformation across the depth also helps the model to generalize well. And this is another work which is my last work in this presentation. This is like, the title is Principle of Least Action Approach to Accelerate Neural Differential Equation. This paper was accepted at ICML workshop. I didn't submitted it's a full. I didn't work on this work completely to submit into a full paper. So the idea is that so we have seen that neural ordinary differential equation considers Doprify, which is a continuous uh, transforming numerical method. So uh, during training, uh, the path chosen by the solver might be a high curvature path. So as we seen earlier, when there is a high curvature, it requires more number of steps, right? So can we reduce the number of steps, or influencing the model to take a simple trajectory instead of taking the complex trajectories? So we looked into principle of least action principle, which is common in the mechanics or dynamics. What it says that, let's consider there's a 2 points between P1 and P2, and the object from P1 want to move to position P2, right? It can take any path, but there is a simple path which consumes, which requires lesser amount of particular measurement compared to all the other different paths. Okay, so in mechanics there is a like when you want projecting a object as a projectile, it takes a particular path, right? uh, so avoiding all the friction and other external influencing factors, it says that the path traced by the object in the motion it minimizes this quantity called action, and the action is given by the sum of the differences between the kinetic energy and the potential energy. It's integral of. So we want to, so it is similar to we want to use this action as a regularizer in our work. So in this approach, we want to penalize the model for learning complex trajectories, right? So during training, let's say these are the hidden representations and these are the accepted time steps by the solver. So we want to consider this as a regularizer, and after doing some manipulations and arranging the words and using the properties of integral addition and Simpson's 1/3 rule, we can compute that integral. And this SR is be used as a regularizer, where alpha is an hyperparameter controlling how much curvature can we accept. So we evaluated the performance of this model on 3 different data sets. So you can see we compared with the 2 different existing models, node and steer model. The steer model, which was designed to reduce the number of steps during testing. And you can see, and this column represents the number of steps required to compute the hidden states. As you can see, the number of steps are compared to low, comparing the existing models without losing the generalization performance. So these are the results for the particular model. So these are my few published works. These are all only related to my thesis. I have some other works in spiky neural networks, which is my first postdoc, which I can share maybe on the upcoming presentations. Thank you.
Really, thanks for sharing, Srinivas. It's a nice range of interesting work. So anyone have questions for Srinivas? From whichever aspect. So maybe I got a question. So I see partially how this neural ODE is related to recently the recent diffusion model where it's very hot and many people are working on. So I can roughly see the connection where is the residual function learning there. And what is your thought about the biggest value we can use neural ODE for diffusion?
Yeah, I was also saying in the previous discussion, I didn't know much about the diffusion models, so I can't comment on that.
So if you go to the for example, one of the residue function where you have the x plus model x equal to x
Yes.
that one, right? I thinking okay, one way to view it is in diffusion, then the x is a denoise. I mean the residual function, the f function fx function is the denoising function. In that case, what would you think about connection there?
Yeah, as I was saying, in diffusion models, what I remember is that they consider some fixed steps as numerical methods, like they are
Yeah.
using Euler or something. I didn't see they are using any adaptive numerical methods, to my knowledge.
Adaptive neuron, okay.
Like Doppler,
Okay.
which where the number of steps could vary depending on the sample.
I see.
This thing I'm not sure.